Hi everyone and welcome. In this video I would like to explain the principles of discrete inference with Pyro. For context, I'm going to explain a little bit how FASTQ files work. So this here is an example of a very small FASTQ file where we can see the typical 4 lines of every read that come out of the sequencer. The first line here corresponds to the name of the read. The second line is the sequence that has been produced. The third line is a plus, and the fourth line is the so-called thread sequencing line. To every nucleotide that has been decoded corresponds one letter in the thread line that gives the quality score or the confidence of the sequencer for that particular nucleotide. The first read here has a relatively high confidence. This has been decoded with high accuracy, but we see here that the second read has got much lower confidence. The letters that correspond here to the decoded nucleotides are very weird symbols that really correspond to a lower quality score on the thread scale here. So this just says that the confidence that the sequence is actually this one here, in the case of the first read, is substantially higher than the confidence that the sequence is this one for the second read. Internally, the way this works in an Illumina sequencer is that 4 colors are recorded for each nucleotide. Each color corresponds to one particular nucleotide, A, T, G, or C. And depending on the quality of the signal, depending on how much one of the 4 colors shines over the others, a quality score is given here. So internally, each nucleotide is decoded based on the data of 4 individual values that correspond to the 4 colors that are recorded by the sequencer. So we are now going to see an example of a Pyro program that will be able to analyze the data that comes out of the sequencer and to make a call for given nucleotides. So now let us see the structure of a Pyro program that can perform discrete inference. By discrete inference, we mean inference where one of the latent variables is discrete, not one of the observed variables. So the one common thing between all the programs where we need to do discrete inference is that there is an unobserved process which is discrete in nature. In this particular case, for the thread detection, what is discrete is the fact that there are only 4 possible nucleotides for any DNA sequence, and we do not observe which nucleotide was actually present in the read, but we only observe the light that is emitted at the different cycles. So the goal of the inference is to guess which of these 4 possibilities is the one that gave rise to the data. So here's the typical structure of a Pyro program with a model and a guide, and we're going to describe the different elements of the model and the guide and explain what is the main difference with continuous inference. As usual, we start with import Pyro and import torch, and then we describe the model. We can see here that the model starts with a plate that is called nucleotides, which kind of gives the idea that we're going to decode every nucleotide independently of each other. And because there is no context outside the plate, this means that the nucleotides are truly independent and not just conditionally independent. The first Pyro sample statement here creates a variable or a parameter that is called NT for nucleotide, and we can see that the distribution is Pyro distributions categorical, and then probs equals 0.25 times torch1's 1, 4. So here this instantiates a vector or a tensor of probabilities, each equal to 0.25. So I'm essentially saying here that every nucleotide that I'm going to pick has the same probability of occurrence as any other. Each of them has a probability of 0.25 to be chosen. So that here creates a sequence of nucleotides that will be the one thing that I'm trying to infer. I'm trying to guess what was the sequence of nucleotides based on the measurements in the light. After this, I'm defining here a constant that I'm calling profile. So this is a matrix that describes the type of signal that we have for different nucleotides. So we can say that the first line here corresponds to an A, the second corresponds to a C, the third corresponds to a G, and the fourth corresponds to a T. And because we're measuring 4 different lights here for different wavelength, we can say that the A here is supposed to have a high emission at that particular wavelength and then a low emission at the other three here. The same goes for the C, the G, and the T, except that each of them emits at different wavelengths. So that gives me the typical profile of observation for the different nucleotides that are present. This is a constant. This is something that we can assume the machine has been calibrated with. Then I define a variable which is called signal. So again, this is a Pyro sample, and this has a normal distribution here. And what's interesting about it is that the location parameters are taken in a way that depends on NT. NT, remember, this is the composition of nucleotides. So NT is going to be a value between 0 and 3, and that will correspond to different rows here of this profile. So I'm saying essentially here that if the first nucleotide was an A, you should take this here as the main profile. If the first nucleotide was a C, well, you should pick the second row. It should be this, which is the main profile, and so on. So if I have a certain number of nucleotides, each of them will have its own characteristic profile given by this matrix here. So the fact that we can select a particular matrix based on discrete values here is really what makes discrete inference different from the continuous case. So at the end here of this normal distribution statement, we also have a two-event one here. That means to say that an event is an entire row here of this matrix. It's not just a 1 or just a 0. In order to estimate what happens, one needs the full 4 numbers that are here. This is so that Pyro does not get confused about what happens, and that it really understands that you have to pick the entire 4 numbers here as the location parameter, and likewise when we give the data, we will give 4 numbers for every nucleotide. And this is it for the model. Now let's have a look at the guide. We can see that the guide defines a parameter here that we call posterior probs. So this is a parameter which is initialized with all the values equal to 0.25. We have one value per nucleotide, and each nucleotide has 4 times 0.25 as the initial value here. And interestingly, we're saying that the constraint in these parameters here is that they should be on a simplex, which also means that we must make sure that whatever values we have here, these 4 values must add up to 1. This is because they define a probability spectrum. And that being done, we have a plate here, which is the same as in the model. We have the nucleotides plate, same shape, and we sample the one variable which is latent in the model, which means not observed. This is the variable NT. The variable signal was observed, and we do not need to sample it in the guide. We take the same distribution as in the model here, the Pyro distributions categorical, and we say that the probabilities of obtaining each category are given by the posterior distribution here, the posterior parameters. So we're going to draw the numbers 0, 1, 2, and 3, not based at random on 1/4 each, but based on the most probable distribution here that we get from the posterior. So this is as usual based on the idea that here in the guide we approximate the posterior distribution, which means that we approximate the distribution that a particular nucleotide was chosen at a particular cycle given what we observe in terms of light. Finally, we have the optimizer, the SVI as usual here. So we take the same optimizer as usual, Adam, and the same learning rate as usual here. The SVI object is defined the same as usual with the model and the guide, so there is no difference here. We finally define the signal that we obtain. So this is simulated data, and we say that, for example, we see these profiles here. We have 3 nucleotides, and each of them corresponds to a light profile, which is 1 row here in this simulated data. We then clear the param store, as usual, and then start doing the SVI iterations until we're confident that we have reached convergence. And finally, we plot the loss curve and we print the value of the parameters. So let's just run this small program and see what we get. So it's interesting here that we see a loss curve, which is not exactly what we're used to. There is a lot of wiggling here, and it looks like maybe it has converged to something, maybe it has gone down, but this is not entirely clear in the sense that actually some of the points were lower to start with and have increased here. So just looking at this profile, we get the sense that maybe something is a little bit unusual. And yet there were no warnings, everything went fine, but we do get the feeling that this loss curve is somehow very noisy. So let's close this, and we can see that here we have the output of the program. We see that we have here the confidence of the most likely nucleotide. And the calls were 0, 1, 0, so that would mean something like ACA, with the confidence score as shown above here. So the inference runs fine, and it looks like we can use it to do this kind of thread decoding, but it would be interesting to understand why the elbow loss was so noisy. In reality, we did something that we should not have done in that particular program. So you can run a discrete program this way, but this is expected that the elbow will be extremely noisy. And so one way to do this is to use a slightly different approach. The first thing that we have to do in order to improve it is to use a slightly different way of computing the elbow. So we have to say that instead of using the trace elbow, we have to use the trace enum elbow here. So we're going to do a complete enumeration. So what does it mean? Is that here in the guide, instead of picking one nucleotide at random according to some posterior distribution, every cycle of the SVI, we're going to try all 4 of them, and we're going to systematically compute the probability that they occur. So that will make the estimate a lot less noisy. And in order to do this, I need to do one more fix, which is to say that I'm going to add a new entry here to the Pyro sample in the guide, and that is to say infer is equal to a little dictionary here where we're going to say that enumerate is set to parallel. So that being done is going to systematically enumerate all the possibilities here for NT, which means A, C, G, or T, or 0, 1, 2, and 3, so that it can really pick the best option every time instead of picking only one of them. And that, in principle, should be sufficient to get a much better quality of the elbow, and therefore a much better estimate. So here we are, we run the same program again, and we can see that indeed now the elbow has been fixed. We have a nice convergence that really tells us that 500 iterations is sufficient. In reality, we even see that about 100 to 200 were probably enough to get a good quality of the approximation. So that is a very spectacular result in this particular case. We can see that all the wiggles are gone and we have a smooth curve. It's also important to say that in this particular case, the inference without the enumeration, the parallel enumeration like we did, was not so bad. In many cases, the inference cannot be performed at all because there's way too much variance and there's not even any convergence in terms of elbow. So now let's see what the estimates look like. We can see that after we fix the elbow, we have higher quality estimates. All of them are substantially higher what we got with the previous method here. And so we'd rather trust these estimates here, even though the outcomes are the same. These ones are much more accurate. So in summary, it's important to understand that there are 2 important fixes to bring when we use discrete inference. The first is to use a slightly different way of computing the elbow, which is trace enum elbow. And the second is that in the guide, we have to trigger parallel enumeration so that we can get this boost to the elbow curve. Otherwise, discrete inference is not that different from the traditional continuous inference. That's what I wanted to share with you today. More from me soon.